Bonjour à tous, and good afternoon everyone. So let's wait one more minute and then we will get started. But first of all, welcome all of you. Okay, so let's get started. So good afternoon everyone, and welcome and thank you for joining us today for the third edition of the MLEAP Stakeholders Day conference. So we are here today within the Airbus facilities in Blagnac. My name is Mathieu Rochambeau. I am the communication officer in the MLEAP project, and I will be today's master of ceremony. So with us today, we have the pleasure to have EASA, which is the contracting authority of the MLEAP project. We have Airbus Protect, which is the project manager. And alongside with us, we have two partners, LNE and Numalis, who also are with us today in the room. So first of all, thank you all attendees for joining, either physically or virtually. I see that quite a lot of you are already connected online, and I see that the room is quite packed. So it's really nice to see you all. And I also see some familiar faces. So for those I recognize, welcome back. So today's conference is regarding the R&T project, which is called MLEAP, which stands for Machine Learning Application Approval. As it is said, this project deals with artificial intelligence and machine learning. So this project was founded by European Union Horizon Europe Research and Innovation Program, on which, like I said, EASA is the contracting authority. And this project has three main tasks, on which LNE is a project, the technical leader on the task 1. Airbus Protect is leading and is in charge of the task 2, and Numalis is leading task 3. So as you can see on the screen, so this event will unfold, the following way as displayed. So this event will last 3 hours. So in between the main topic, we will have a coffee break, a 10-15 minute coffee break. Then we'll come back to the room to continue with the presentation. So we will start with the introduction of the partners and the MLEAP project. Then we will have the presentation of the MLEAP roadmap according to EASA objectives. We'll have a review of work result research and presentation of experimental analyses. Then we'll continue with the generic end-to-end AI development pipeline proposal and the joint conclusions. Then we will continue and end the event with the key takeaways and the MLEAP project next step. So as you can see on the screen, we have put a Q&A session in between the major topics. So what we will do, so we will take 10 to 15 minutes to answer any of the questions that you may have. So to ask the question, it's quite simple. So for those who are online with us using the BlueJean tool, the video conference application, just directly type your question within the Q&A section part, and then we will try to answer as much as we can within the time frame that we have. For those of you who are with us in the room, we will pass out microphones, then you can directly ask your question to all of us. And then we will end the event with an afterwork. So for those of you who want to stay and continue the exchange with the MLEAP partners and the team, you are welcome to do so. So just right outside of the room, we will have food and beverages that awaits for all of us. So we would really appreciate if you could stay with us for this. So this event is recorded, and the presentation and as well as the recording will be available on the EASA MLEAP page and as well as on the Airbus Protect MLEAP page. So we'll publish this, the link and the presentation shortly after the presentation. So before we get started, I really like to thank all of you, first off for being here, and also for the interest that you have shown in the MLEAP project over the past few months. And as you know, the MLEAP project has been going on for almost 2 years now and will end in May 2024. So quite shortly. So this is just the disclaimer pages. And so now let's continue with the introduction of the MLEAP partners. So as I said today, so with us on the EASA side, we have Xavier Henriquel, we have Guillaume Soudin, and we have here François Triboulet. On the Airbus Protect side, we have Thierry Belkacem, we have Jérémy Bascan, we have Jean-Baptiste Rouffet with us, and myself, but I already introduced myself, so my name is Mathieu Rochambeau. So on the LNE side today, we have Sven Ribeiro. And on the Numalis side, we have two colleagues, so Arnaud Uerlen and Noémie. So let's carry on with the introduction. quickly with the MLEAP partners. So Numalis is a French state-owned institution tasked with the coordination of French meteorology and the testing and certification of various products, including AI system. Numalis is a French deep tech expert in formal methods, providing industry state-of-the-art standards and technical solutions for AI explainability and validation. And so Airbus Protect is a risk management company specialized in 3 domains of expertise, which are safety, cybersecurity, and sustainability services. So I will go through, I went really fast through those slides, but like I said, the replay will be available as well as the slides, so you will be able to, if you want more insight, to have a look at them. And so now let's continue the presentation with the presentation of the MLEAP objectives according to EASA roadmap. So Guillaume, floor is yours.
Thank you, Mathieu, and thanks to Airbus Protect and to the consortium for welcoming us here in Blagnac. Thanks everyone for participating here. So good afternoon, and online maybe good morning. So before jumping into here, you can see the EASA team with faces and names, and you will see the people anyway live. So that's a great thing that we could come, the 3 of us actually, the 3 main actors of MLEAP in EASA. Before jumping in more details or technical details within MLEAP itself, what I will do is to provide a bit of a step back and looking at the big picture, why we started MLEAP, what in the EASA AI roadmap and program we were looking for in the big picture of the activity of what we call the EASA AI roadmap, which now is at version 2.0 since May last year. May 2023 was a time to update our initial roadmap from 2020. That first roadmap actually has brought us to conduct a first phase of exploration, which is ending now. We enter in the phase 2, as you will see on the next slide. And that's a really good time, I would say, for us to also have the results from this MLEAP project to actually inject concretely into the rulemaking that will start this year on the other side, everything that is really relevant to take into account on the learning assurance process in particular, because that's the main focus of MLEAP. The reason for updating the roadmap, you can see it here on the slide in 3 main drivers. Actually, the first driver was the extension of the technical scope. We started machine learning, deep learning, which was the focus brought by our industry to us as a challenge, let's say, as a new challenge to take on, which we did with the initial roadmap and with the initial set of concept papers that we published. Now we see industry also coming with revival, I would say, of symbolic AI and the capacity also to hybridize different approaches. That's something we will work on later. It's not in the scope of MLEAP anyway, so just to mention at least this extension of the scope coming. The updated timeline, it was a time to update the prognostics that we had from industry, but also to augment the action plan. This you will see on the next slide. And the third point, which is extremely relevant to MLEAP, is the anticipation of what we call the consolidation phase, phase 2, with an overview in the roadmap 2.0 of what we call the rulemaking concept. So that will be turned into a plan. We will refine the plan this year. We will start a rulemaking task. So all things coming. For looking at the overall timeline of the roadmap, I think this picture is really well known by probably most of you. It was the same picture in the roadmap 1.0. We updated slightly again the prognostic at the bottom. You can see a bit more horizon for going into more advanced automation levels, but we still have this notion of phases. The phase 1 is ending now. The big deliverable of our phase 1 is definitely the concept paper for level 1 and 2 guidance. The concept paper is a maturation document or document in maturation that captures the big picture of what we expect and anticipate in terms of objectives and requirements for certification and approval of safety-related applications. Yet, of course, it's not a final view, but it's a very strong reference to enter in this phase 2 consolidation, which will inevitably start the phase of rulemaking, meaning really turning this set of reference into a meaningful set of rules and also, of course, acceptable means of compliance, AMCs, and guidance material, GMs. So that's something we will keep really in line with the presentations we will do today, also in the presentations of my colleagues. And that's where MLEAP actually will flow into first anticipation of the concept paper, but also definitely in concrete steps in the rulemaking steps. To talk about rulemaking, I just brought this picture we have in the roadmap 2.0, which is a very important picture. It sets the big scene, I would say, of where we, EASA, are, let's say, gathering our effort or bringing our effort. So at the top, of course, the EU AI Act that is in preparation and in final preparation is the main driver. It requires from an Article 81 to update the EASA basic regulation to take into account the provisions, the technical provisions for the high-risk AI systems, which we'll do, I would say, already in the scope of the concept paper, and we will do definitely in this step one of rulemaking by creating what we call a Part AI to gather the authority requirements, the organization requirements, and the extremely top level, I would call them technical requirements here. And then most of the concept paper will be translated into a meaningful set of generic AI-related AMC and GM, which in a step two of the rulemaking will be instantiated domain by domain at the level of the regulations and or complementing the AMC GM that are already in place for, I would say, for each domain. When I say domain, I mean product certification, initial airworthiness, ATM, aerodromes, etc. So it's a comprehensive work we will have to do, horizontal, of course, in some way, taking into account the vertical specificities. And at the bottom, we represent a very important part of the work, which is the working group efforts. There is a EuroCAE SAE joint working group 114 G34 that is well known to probably all of us, working extensively today on the learning assurance building block and scope, extending the scope also to the human factors for AI block, which is one of the novelty in the level 2 guidance, and that's something to be also worked on together. And definitely the message is looking also at what is happening on Sensenelec and ISO side to have a meaningful way of gathering detailed means of compliance and bringing them, plugging the, let's say, recognizing them at the right level within our AMCs and GM material. So that's a really comprehensive view, very important to keep in mind, and MLEAP is definitely a brick, let's say, that will flow into this framework. To finish the big picture, the concept paper, I will not enter in any technical details, but it contains the technical guidance, technical objectives, and provisions for organization requirements that we've gathered and understood so far in interaction with all our stakeholders. We gathered on the proposed issue 2 more than 900 comments, so it was a hard work last year to try to complete this on time for the end of the year. We finally pushed the deadline for end of February 2024 to publish the confirmed and final issue 2. That's coming very rapidly. And you can see the diversity of stakeholders that are really interested in this work and actually helping us a lot to mature. So many thanks to all involved in the commenting. And to finish, here's the big picture. Nothing could be done by EASA standalone, in isolation, definitely in all what you can read in the concept paper. Our work was initially the roadmap, of course, to enable the effort, and that was our big initial work. But the concept paper itself is the fruit of a lot of collaboration, stakeholders, use cases gathered in different partnerships, research, innovation partnership, but also from concrete certification projects already started. And with all these stakeholders and the working group effort at the bottom, we have a real, I would say, extremely iterative and dynamic interaction that helps us to get in the concept paper, I would say, the best mature and consolidated view we can get at this point in time. Research is also flowing into the framework, in particular MLEAP, but also a number of research on CISAR 3 and Cleannovation is also bringing a number of AI-related topics. So that's the big picture, and I give you the floor, Xavier, to dig into MLEAP specifically.
Thank you, Guillaume. So as Guillaume was saying, MLEAP is one of the R&D projects that we use to mature the AI/ML guidance. So maybe a reminder about how we've structured the EASA concept paper. It's structured on 4 building blocks. The first one is the AI trustworthiness analysis. First, we request to characterize the AI application before having a safety assessment, a cyber security assessment, and some ethical objectives. We have a second building block that has to do with what we call AI assurance, mainly to deal with learning assurance and development explainability. The third building block has to do with human factor for AI. And this is one building block that we have extensively reworked in the issue 2 to deal with some challenges that come with level 2 AI, like human AI teaming and the modality of interaction. So this is a part that is evolving these days. And the last building block is what we call the safety risk mitigation. This building block is a technical possibility that we give to mitigate some objective in the other building block that would not be fully complied with. So if for some reason some objective in the AI assurance block or in the human factor block cannot fully be met, we have this safety risk mitigation building block that allows to implement some technical mitigations. MLEAP. So the concept paper is touching on a number of technical topics, and MLEAP is specifically focusing on the learning assurance aspect in the AI assurance building block. So the MLEAP project, as I was just saying, is focusing on the learning assurance objective to help us further refine or identify concrete means of compliance for the objectives in the learning assurance building block. It's a project where EASA is a contracting authority, so we are performing contract and technical management on behalf of the European Commission that is funding the project. It's a 2-year project. It's been granted to a consortium, an ad hoc consortium, that is, as Mathieu was explaining, led by Airbus Protect, with the participation of LNE and Numalis. We have 3 technical tasks. Each task is allocated to a member of the consortium. Task 1 is dealing with data. It's executed by, led by LNE. We wanted first to focus on data because this is one of the main source of cost for development of AI project. And some of the characteristics that we believe are important for certifying AI, like data completeness or representativeness, or when we launch the project, we are missing some recognized tools or methods to get some confidence that the data sets are either complete or representative. So this is why we first focus a part of MLEAP activity on data. The second technical axis for MLEAP was generalization. Generalization is an active field of science. We are seeing a lot of articles being published on a very regular basis. And it's important for certifying or approving an AI ML application in aviation, because not only we want to make sure that our AI system is working on the test data set, but we also want that in service, when it will be using unseen data, the level of performance will remain acceptable. And the third technical axis is the robustness. In case something is evolving in the training algorithm or in the operational environment, we want to get some guarantee that the AI ML system output will remain, let's say, the same to some extent. It's also a domain where we saw at the time a lot of publication and a variety of methods, either purely empirical, statistical, or based on formal methods. And we structure the project to investigate these methods further. And this part of the project is being led by Numalis, that has certain expertise in terms of formal methods, and that has been over the last 20 months investigated this aspect of the project. The last axis for the project is related to EASA getting more experience with a complex AI project. And what we wanted through this research project is get some hands-on experience on complex aviation use cases. This is why in the last phase of the project, we asked the consortium to to investigate the methods that they have identified on concrete aviation use cases. And this is what is coming in the coming months. Going a bit into the details of the learning assurance building block and where we expect MLEAP to bring some concrete means of compliance. I will first remind the W-shaped process that is structuring the AI assurance building block. The fundamental question we are trying to answer with AI assurance is whether the system will perform as intended with sufficient guarantee in terms of generalization and robustness of the AI model. And to do that, the AI concept paper is building on traditional development assurance techniques and visiting all stages of a learning process. If you are familiar with the W-shaped process that we've been promoting over the last few years, you may notice that this diagram is slightly different from what we've presented in the past. We've been refining the W-shaped process in the issue 2. And the dotted line that represents when activities that are specific to AI are happening is now one stage up, because we, through discussion with the various stakeholders and through the first project, we get convinced that as soon as we start deriving requirements for the constituent level, there are activities that are specific. Typically, the specification of the ODD is something that we don't necessarily see on all aviation's applications these days. So the first step is to derive requirement for the constituent level. The second step in the W-shaped process has to do with data management. That is a crucial step before moving to objective related to learning, verification of learning, which makes the first part of W, before moving to implementation and verification of implementation. And in this framework, when we prepared the project, we identified that for each of these blue boxes, behind each of whose there are some objectives, the MLEAP project could bring some further insight on what could be means of compliance. And you can see how we mapped at the time the various tasks of MLEAP. In red, the data, in green, generalization, and in dark blue, robustness. And to complete this introduction by EASA of MLEAP project, just a reminder about the planning. So we've been, as Mathieu explained, working on MLEAP project for the last 20 months. It's a 2 years project divided in 4 phases. At the end of each phase, we had a stakeholder day, stakeholder day number 3. Last year, or 2 years ago already, in November, we had the first event. The major event for the project so far was in May, when an interim public report was released, as well as an executive summary. So later on, you can find these reports online. And if you want to get more information on what has been achieved so far, I would advise to start with the detailed executive summary, because it gives a good introduction of what has been achieved so far. In the coming next 4 months, we will start the experimentation on actual aviation use cases. Earlier today, we were at Airbus Protect headquarters, and we could see the hardware that has been put in place to run this experimentation. So it's going to become much more concrete for MLEAP in the coming days or weeks. And there will be a final event at the end of the project in May 2024. So a final public report that is an evolution of the first public report will be made available by EASA. And a couple of days after, we will have a dedicated day during the EASA Days 2024 to present for the consortium, to present the result of the project. And with this, I would be happy to take any question if you have some on what we want to achieve in MLEAP.
So thank you, Guillaume and Xavier, for this first presentation. In the room, is there any questions? So there is a microphone here, so we can pass it out for some of you if anyone wants to ask a questions. So any questions so far? Okay.
Say Gary. Hi. Okay, thanks for that, Guillaume and Xavier. So I'm Gary Brown. I work at Airbus. So I'm supporting in G34 and G57, SG57. So the question I have is, we've determined that we need a use case 2, and then you're talking about use cases here. So is there a correlation? Is there an overlap? Is there an opportunity? Because it seems like, Airbus Protect are moving forward for doing experimentation and doing a use case. Airbus Protect are also safety. So I would like to understand if there's an opportunity.
Yes, thank you for the question, Gary. Maybe for the audience to explain what is use case 2, because it's really specific to the working group. So the 114 G34, we have a use case 1, which is the TBS, the time-based separation, that we started investigating to look at this connection between, I would call them the quantitative safety objectives and the performance guarantees, performance measurements we can perform on a specific application. And this is a real question within the group. We oriented in the concept paper a concept where there would be a connection, and that would be actually great to have one, because that would set the scene for really measurable and the anticipation of how we connect results from performance measurement and generalization guarantee or generalization bounds anticipation to the safety. That's a concept, I would say, and that's one of the things that we have as a big discussion within the working group. Is it practicable? Is it feasible? And we know all the limitations that will be touched upon on the generalization guarantee side by the colleagues from Task 2. So connecting to that, we said in the working group, what we're missing is actually another use case, the use case 2, that will provide a lot more, let's say, capability to assess this question, to have real data, to have real, I would say at least a use case with safety objectives, real data, and capacity to get figures and really quantifiable aspects, and to see where is the connection. So this is one of the things we are doing in the working group, and we are heavily supporting on the other side. To answer your question now, I think there is another opportunity indeed to see what those use cases we have in the MLEAP are bringing us in this direction. So you will see a bit more about the use case, I would say, in the presentation, but definitely we have some computer vision and natural language processing aspects in 2 of the use cases. The other one being the famous AK6U. Probably the AK6U will not help solving directly this question, but the 2 others could really bring another opportunity. Yet I would not wait for that in the working group, just to finish the answer. I think we still need something, let's call it a bit simpler than the real size use case we are investigating in MLEAP. It's not necessarily a toy use case, but something a bit more, let's say, smaller in terms of size and scope, so that we can go to something that is a bit more intuitively demonstrating what we are looking for, because we are also eager to progress on that in the working group. So that would be my answer. I don't know if you have a follow-on.
That was a good response to the question. I think I'm not looking to replace what we're doing in the working group. It was more like an independent look from the MLE perspective, tailored for safety. Because my fear is that use cases are more trying to see if it's fit for purpose, looking at qualification, can it achieve what it needs to achieve? But really, like you said, for the question on quantitative safety assessment realization, we need to look at something simple and tailored just towards safety. So we need to take away this concept of fit for purpose. We need to just focus on, well, how will I influence the development? And at the end of the day, will I be confident as an applicant and you guys as an approver? So we want to keep it simple. That's key. But there's an opportunity, I think, in parallel and independent for MLEAP to focus on the safety bit and not just focus totally on, I give you something that can do the job. Thank you.
And if I may add on Guillaume's answer, when we looked at the use case selection, it was really our initial intent to find aviation use cases that we could share with working groups. The challenge that we are facing is if we want to do something interesting and complex in aviation domain, well, the industrial partner or the consortium may have some limitation in the type of information that they are able to share or willing to share, because there are some strategical data or some strategical type of model that they may not be able to share with the public. So we ended up, instead of selecting of working in the phase 4 only on one use case, working on 3 use cases. And one of the reasons why it's interesting to have 3 use cases is that we can have AK6U, that is well known to the community. But we also wanted to investigate complex aviation use cases. And so, complex aviation use cases, AK6U is a complex aviation use cases, but we wanted to look at other type of complex aviation use cases, like vision-based, or the second use cases in ATM domain related to speech recognition. So we made a trade-off, and between what was feasible, available, and would meet industrial constraints. AK6U result will be part of the public report to some extent. For the other aviation use cases, we will have some results to present, but we will not be able to go in the level of details that I believe will be sufficient for Work Group 114 to work with. So one thing we did for this conference is that we prepared some example on what we call toys aviation use cases that are public. And in the follow-up slides for the rest of the presentation, you will see reference to many toy use cases, but they are not related to aviation. So to come back to your question, I'm not so sure that some of these toy aviation use cases can be directly used by Working Group 114. However, in the past, we also worked on IPCs, in particular with Dedalin. So I know that there is an ongoing discussion in Working Group 114 to select what kind of aviation use cases could be selected as use case 2. And I guess it will be a discussion next week in your OK to see what could be aviation use case 2.
Just finalize the compliments, I'm sorry, but just to water down too much expectation, the scope of MLEAP definitely on what you will see also in the technical presentation is not on the quantitative safety assessment. It's definitely more for task 2 at least, just taking this one, giving the direction on what means could be used in order to provide those generalization bounds and guarantees that we are looking for. So, but the use cases can have a merit absolutely to help out. Any other question?
There is no questions online so far. So if there is no more questions here in the room, we can carry on with the presentation.
Okay. So, thank you.
Thank you, Guillaume and Xavier. So let's continue with the presentation with Thierry on the review of work research results and presentation of experimental analysis. So okay. Thierry, floor is yours.
Thank you. So hi again, everyone. And so before carrying on into the presentation of the experimental results, let us just say some additional words about the MLEAP project objectives from another point of view, focusing more on the technical details. So as already mentioned into the AI roadmap by the ESA, there is a set of issues related to the AI applicability and use. And the MLEAP project was launched in order to provide some ways, some technical elements in order to help, in fact, the ML technologies integration into safety-related applications, mainly on safety critical use cases for aviation. And focusing on that, so we made a detailed analysis of the objectives on the concept paper by the ESA and also through the different exchanges that we had with our interlocutors on the ESA, and identified the main workflow, in fact, to implement the different activities. So starting from the analysis of the state-of-the-art related to the different objectives that have been mentioned on the project statement, but also in the concept paper, and what we would like to verify in terms of data quality, generalization, but also the performance stability and robustness. In addition to the selection of the relevant use cases for the MLEAP project. This first step focuses on the analysis, identifying the main issues related to the applicability of several methods, how we could select them, how we can use the existing elements from the state of the art, but also in order to analyze in a fine way the different use cases. By the end of the first step, a set of methods have been selected for the different tasks, including the data qualification, the generalization, assessment, and evaluation, and the learning also, but also the last part concerning the robustness and the stability analysis. As already mentioned, so we have used for the first experimental results a set of toy use cases where the objective is to assess the applicability of the different methods and have a big picture of their features and compare their behavior into the different tasks. And we have initiated a generic pipeline that has been already presented in the previous events. And on the third last step of the project, which is the current step and until the end of the project, we are on the phase of applying the different hypotheses and the different selected methods to the toy use cases, but also to the real aviation use cases that have been selected, while completing also the generic pipeline that we have already presented in the previous step of the project. So I'm not going to present in details the pipeline because there will be a dedicated session later this day. And just to say, in fact, the main outcome of all this work going into the 3 different steps, analyzing and implementing the different stuff in the workflow of MLEAP, we have completed so far this pipeline, which represents, in fact, the implementation of the W-shaped learning process, where the objective is to help out the different stages of the development to find the elements that could help or not your development of AI into the industrial use case, and how this can be achieved by the end, and what are the main elements that you need to pay attention for or may be avoid in order to boost the performance of your model. So more details will be presented on the different 3 tasks. So concerning the selected use cases, so as I mentioned, we have used 2 kinds of classes. So there is a wider list of the toy use cases that are more simple. And as I said, these are not especially aviation use cases, but these are simplest and simpler, in fact, use cases compared to the real use cases on the right, where the objective is to compare the behavior of the different methods, assess their applicability to the similar, in fact, kind of data in terms of analyzing the images, the NLP application, and so on. And after this preliminary analysis, we apply the same, in fact, analysis, but in a more rigorous way, of course, to the real aviation use cases. And these 3 real aviation use cases, stating for ATC SCT, which is the air traffic control speech to text, here the objective is to help the translation, in fact, of the spoken instructions by the air traffic controllers and help, in fact, the interpretation or maybe avoid the mistaking some instructions. And in the second use case, the AVI for aircraft, which means the automatic visual inspection of aircrafts, it is a use case that is made to help the operators analyzing the skin of the aircraft and find damages. The final objective of the project that provided us with these data and the use case is to find, in fact, the damages that are more urgent to be solved, for example. And the final one, which is well-known, collision avoidance AK62, which is, in fact, self-defining, I guess. And without more details, I think I will let the floor to the different tasks to present in more details the analysis on the experimental parts.
Okay, hello everyone. So I'm Zen Ribeiro and I'll be talking about task 1. Task 1 is about data completeness and representativeness. So First, let's define both concepts. Completeness, we define completeness as a dataset that sufficiently covers the entire space of the ODD for the intended application. And we consider a dataset as representative if the distribution of its key characteristics is similar to the actual input space of the intended application. So with this in mind, the workflow in task 1 was first to draw a state-of-the-art of all the available methods and tools that would allow the assessment of either completeness or representativeness that existed in bibliographical references. So we identified more than 80 sources for that. Then we synthesized these sources into what we call the selection grid that identified 19 methods that would be further tested in the project. And in the later phases of the project, we experimented a lot with all these methods to see what we can get out of them. So I'm here to present you the latest results of our experiments. So today, the first method I will be discussing is actually an off-the-shelf tool that you can download and manipulate. It's called the CleanLab, and it's already in use in the industry by companies such as Google or Tesla. So it's quite a prominent tool, and it's mostly open source. We started our preliminary experiments with the MLEAP dataset. So CleanLab is used to detect outlier, near duplicates, and labeling errors. For outliers and near duplicates, the feature depends on the model that you provide. If your data are non-tabular, so the MLEAP dataset is non-tabular, it's images, and labeling errors are always model dependent, and this dependence of the model is an important aspect of the performance of CleanLab. That's why we trained two classifiers, one with a 97% accuracy, so a very good classifier, and one with a 75% accuracy, significantly less good, to do a contrastive study on how it impacts CleanLab's behavior. So for the outlier experiments, so in the green box, you have the 97% accuracy classifier. And in the orange box, you have the other one with 75%. So on the leftmost column of each box, you have what CleanLab considers as outliers. So basically, on the best performing classifier, you can see that the outliers are indeed kind of strange instances. For example, what is supposed to be a 3 is probably not very exploitable. And by contrast, if you look at the orange box, the outliers identified by CleanLab are pretty clear examples. So it's more of an artifact of the model behavior rather than a real outliers. So moving on to mislabelings, you have the same idea, green box for 97% and orange box for the 75%. On the middle row of the green box, you can see a sample that is classified inside NIST as a 3, and CleanLab suggests to reassign it to a 9, which seems reasonable. But the other examples are mostly hard examples, but you would tend to be more in agreement with the initial assignment. Whereas if you look on the orange box, it's clearly not bad examples, no mislabelings. They are all 6, and it's not very problematic. So once again, we see that it's more that CleanLab's mislabelings are more a reflection of the performance of the model rather than real information on the state of the dataset. And the last example are the near duplicates. So again, if you look at the best performing classifier, all the suggested samples are near duplicates of each other. They are all ones with a slightly tilt on the right. Whereas for the orange box, the worst classifier, all of these numbers are supposed to be near duplicates of one another, so less convincing. So the takeaways for CleanLab is that it's a really interesting tool actually to identify edge cases, hard cases from the model perspective, and also identify correctly interesting mislabelings if your model is performant in the first place. And this model dependence will help you to tailor the data to the model. So that's really interesting to have a feedback from the model and enhance your data based on what the model makes of it. The downside of this model dependence is that you will require a mature model to have a good insight. So a mature model is closer to production, and moving back to the data set closer to production is more costly. So it's a trade-off. And finally, all this analysis has to be performed by a human, which means that the larger your dataset will get, the more manpower you will have to put, and it will also be more costly. So once again, it's a trade-off about what you will get and what you will put in. The second method that I want to discuss today is a risk-based method initially designed for demographic data, proposed by the Business Software Alliance. So just to be clear, the BSA framework defines an entire life cycle of AI application, and we will be focusing only on the first step, that is data acquisition, where the evaluation of the representativeness of the data is discussed. So the other steps are not in our scope. So the first weakness that we found in the framework is that there is no real homogeneity between the checkpoints, which are basically BSA's version of requirements for the assessment of the dataset representativeness. So, for example, two checkpoints are to compare the demographic distribution of training data to the population where the system will be deployed. The second one is assess whether there is sufficient representation of subpopulation that are likely to interact with the system. So the first one is very broad. It requires a high-level statistics and a large comparison, whereas the other is really more narrow and would require a more fine-grained analysis. So what we propose to make it a more let's say rigorous tool would be first to change the wording to hint about the required results. So, for example, moving from comparing distributions and assessing whether there is a sufficient representation to to notions like close similarity and sufficient representation. And to complete this wording with more clear and detailed instruction on how to achieve these objectives. For example, using relevant statistics, expert analysis based on the context of the data set. So one disclaimer is that basically the entire framework is not magic. It will only lead to estimated result, and there will always be a part of uncertainty. So for the experiment on applying this framework, we used a dataset that we have at LNE, that is the ROSE dataset. It's basically a dataset for weed detection, and we transposed the first checkpoint to the families of weeds, which can be analyzed by classes or samples, and the second checkpoint was applied to species that again can be analyzed from a class or sample perspective. So if we just to give a quick example of what we can get from the method, if you analyze the weeds by the classes of families, you can compute a representativeness ratio. So basically the number of families in the dataset versus the number of families in the target population, which is Europe. You would get for the ROSE dataset the result of 0.08, which is non-representative. So you know that your dataset is not representative. We know it. And that's one of the main problem with this notion of target population for comparison, is that either they may not exist. For example, for the ROSE dataset, we don't have large information on the weed species distribution in Europe to exploit. And sometimes the data can exist, but the choice of data might not be evident. The example that we develop in the report is the case of the VoxScream dataset. So it's a voice identification dataset for identifying the voice of people to see if they are the same in criminal records. So basically being able of judging whether the person committed a crime or not based on their voice. So the statistic that you might want to use is either the demographics of France, because it's a French project. And in this case, you would have the question of the ethical dilemma of using the demographic of France. So you hypothesize that anybody in France can be a criminal, which is ethically discussable for AI. Or you can use the French prison statistics, but in this case, you would have a selection bias because you would be using the voices of people that have already been convicted. So sometimes you can have this dilemma. Sometimes you can have more than dilemmas. You can have you can be prevented from using certain data, and BSA doesn't anticipate this problem at all. So that's a blind spot. And there is another blind spot, that is this notion of fairness when using, for example, the demographic of France versus the prison statistics. And the notion of fairness is not well addressed in the framework either, because the basic idea of the framework is to, at design phase, select appropriate fairness metric, then evaluate the representativeness of your dataset, which is completely unrelated. If your dataset is unrepresentative, rebalance it with either additional or synthetic data. And then you train your model and you evaluate it using your selected fairness metrics. And if you do not have fairness, you basically go back to data acquisition. So you lost time and money making a representative dataset that is completely voided by the fact that it's not fair. So that's the point of this slide. Basically, you have this situation where you put energy into building a representative dataset. It's not fair, and you basically throw it in the garbage, which is not anticipated by the framework and is very limiting. And the alternative that we propose, either instead of just being able to rebalance your data for representativeness, you can also consider to reduce the scope of your use case so that your dataset is more appropriate to the use case that you're working on. And that's what we did, for example, for the ROSE dataset, considering that we could have access to statistics regarding only 4 species of weeds in Europe. So the key takeaways that we have so far on completeness and representativeness is that there is a need for a priori assessment. This a priori assessment would be based on the ODD, but then there is also a need for an a posteriori assessment based on the feedbacks on the model. So there are two checkpoints to use, the ODD and the model. And the next step will be to apply all the methods that we already discussed here and in the report on the MLEAP use cases to provide more concrete examples of what we can do for completeness and representativeness. So I'll leave the floor to you. Thank you very much.
The second task of the project is dedicated to the generalization property, with the objective to identify and develop, let's say, efficient methods and tools for quantification of generalization assurance level in generic use case, in generic case of machine learning, deep learning development. To do so, we are testing available methods and tools to evaluate generalization bounds, highlighting the barrier and generalization guarantee for a given model, and the identification of means that could promote the generalization. Supervised machine learning, we are using a training dataset to optimize the parameter of an algorithm to minimize the error on a training dataset. What we are expecting is that our model will continue to keep good performance level and behavior on unseen data. This is based on the assumption that behind the data we have some regularities which are discovered during the training phase. To assess the generalizability, there is different means. We can, for example, perform some measurement on test dataset which has never been seen during the development process by our model. But we can also, thanks to the generalization theory, assess the generalization quality and identify some good models. But we can also use the generalization theory to provide some guidance concerning the development process. But we can also, and thanks to the identification of the main driver influencing the generalization, minimizing or maximizing, let's say, the probability to achieve a good generalization. And my presentation will focus on experimental results on generalization bounds and also on the key drivers that are influencing the generalization. Our experimentation has been done as follows, with the objective to test generalization bounds as a means of compliance to answer some objectives we have in the concept paper, and also to check how the theory behind the generalization bounds can help us to identify a good architecture for a given task, a given objective. Our experimentation here has been done on fashion means dataset, which are a picture of Zalando's article classified. We are testing two different architectures, a fully connected neural network and a convolutional neural network, with a priori estimation. So before the training, we apply the bounds to see if we can have an idea of which model will be the best for the generalization concern. We have tested and trained several models, and we have analyzed, after training the model, the a posteriori application of the bounds to see if we can have some statistical guarantee concerning the capacity of the model to keep good performance on unseen data. Here I present some results within the two tables. What we can say is that the a priori evaluation is very pessimistic. We're expecting some value close to 0.1, 0.2, and as you can see, we are far above this objective. Why it is very pessimistic? Because it is before training, the theory should remain valid in the worst case. So when I completely fail in the optimization, then of course it is difficult to have a tight bounds. And what I can say also is that whatever the theoretical framework we are using, based bounds, complexity or margin based bounds, we always have the same tendency that we are promoting the minimum parameter within our architecture, which finally come to the VC dimension conclusion we can find there and there. After the training, we have applied also the generalization bounds to see what we can say. First thing that, of course, we have a tighter bounds. It is a naive application, meaning that I don't use the theory to drive my development process, to drive the kind of optimization I should do. And the results are still above what I can expect to provide good or acceptable, let's say, guarantees concerning the performance of my model in the generalization activity. In terms of my takeaway, so for generalization bounds, it is difficult to obtain the tight bounds with naive application. Nevertheless, when you check the theory, it keeps some highlights and some key elements that can be used to boost generalization, such as the regularization, so the level of dropout you can put in your network, the batch size, the early stopping and optimization methods, and also the pooling criteria you can have in convolutional neural network. we don't succeed with the Boons application in a naive way to have a good guarantee or acceptable guarantee. Then we have analyzed some possibility, some alternative to support the overall safety analysis. The architecture and the hyperparameter selection, such as the uncertainty quantification, the conformal prediction, or the cross-validation. In terms of next steps, we'll assess the development workflow impact and the boons with a non-naive application of those boons. We'll apply the theory on the Airbus use case to see how what we can bring depending of the real industrial use case. And we'll analyze the generalization with regard to the data preparation and the analysis of the data, what we can bring when we are mastering properly the data, and we'll do the link with task one, with when activities. Now, jumping to the key elements that are, or key drivers that are influencing the generalization. So the next use case or next implementation has been done on the air traffic control speech-to-text, where the objective is to correctly translate spoken instruction to text, and we had a target of 10% maximum word error rate. For that, we have used two different datasets, one which is a Airbus dataset with real ATC exchange, but only for French airports, and an open source dataset done with European airports. We have tested two different models, and after the training, we obtained the result you can see on the table. And the main takeaway, or what we can say here, is that clearly we are not at the expected level of performance. And after analyzing of the pipeline, it is clear that the Airbus model trained with the Airbus dataset is not performing at all with the correct behavior on the open source dataset. So there is a clear lack of generalization that we can say it is due to the lack of representativity in the data, not enough accent, not enough airport, and so on. Also, there is the audio quality, what are the microphones which are used, what are the noise we have, and we have also the model. You can see that when we go from VOSC API, which is a Caldi model, to transformer-based model, we can improve the performance. Nevertheless, in our use case, industrial use case, there was a constraint to have a good performance in real time. So meaning to not have a too heavy model. And then at the end, what we can say is that there is a balance between what we want operationally and what we can achieve in terms of performance. In terms of next step, we'll fine-tune, adapt the training and the optimization phase to answer the different machine learning module objective, especially concerning the balance between the real time and the performance. The next experimentation has been done on AVI. AVI is for automatic visual inspection, and here the objective is based on a picture of the aircraft to identify automatically the damage we can have on the skin of the aircraft. So the damage, there is two categories that has been selected: the dent damage and the lightning strike impact. Here we are using Airbus image database, which has been classified and labeled manually, and we are using a well-known YOLO V5 model, which has been fine-tuned to minimize three kinds of error. So the first error that we try to minimize is the damage location and the damage dimensions, the classification error, and also the no-object error. What you can see in terms of result is that we are far from the target, which was 95% accuracy. We can see that we are at 41 for the lightning strike and 62 for the dents. This is mainly due to the low level of data available. So clearly it illustrates the fact that we need to have enough data for the training phase. And also when we analyze what can be improved, we see that the loss function don't enable us to easily compare the result with other models. So it's for that in the next step, we'll use the data augmentation with simulated data to increase the volume of data with, and we'll take care about the bias that we can introduce by the simulation data. And we'll use models that will enable the segmentation, which will be the YOLO V8 model. Finally, the last experimentation that I want to show you is concerning the AKC-XU, which is an anti-collision system. And here the objective was to reduce the size of the lookup table by a huge factor. So meaning that to perform the same activities and what we can do with the lookup table with a neural network. Here the main concern was to have 100% accuracy. Of course, if I want to decrease the risk of or to eradicate the risk of collision between several aeronefs, then I will need 100% accuracy. Here we're using 45 neural network, and it was also a challenge for us to see how we should take that into account in our generalization approach, when there is not only one big neural network, but several ones which are here in parallel, and how to deal with that concerning the conclusion we can make for each individual neural network, or do we have to consider the overall as a black box, and after to make our to run our conclusions. What we can see, we achieve a good performance, and nevertheless we are not at the 100% level. Main reason is the data imbalance. We have a lot of clear of conflict classes, and so that don't provide enough power, let's say, during the optimization process to the other classes. What we can say is that the model architecture has been well selected versus the classification task. And in the next step, we'll try to change a bit our approach to limit the unbalanced dataset impact with weighted loss function or with data augmentation. Because in the lookup table, finally, we can artificially add a new line for the class which are not clear of clearance, clear of conflict, and then artificially increase the size of our data set. In terms of conclusion for this part, I would say that the generalization bounds with a naive approach or naive application of generalization bounds, we have not been able to provide accurate and self-efficient means to guarantee the generalization of our used model. But nevertheless, the theory confirms that there is some key elements such as regularization, early stopping, or optimization methods, and the pooling that can support or promote, let's say, generalization. In terms of limitation, we can see that weak data processing and lack of data for optimal training is clearly something that has to be clearly analyzed and to be demonstrated. There is also some limitation when we have a gap between the training objective and the selected measure we have. And finally, the model selection, there is a balance between the architecture selection and the different business needs we could have. Thank you. I will hand over to Arnaud.
All right, thanks. So hi everyone. So let's talk now about task 3, which is about algorithmic and model robustness. So in this phase, we focus mainly on identifying source of instabilities during the design and operational phase. And previously on the MLEAP project, I've presented this kind of figures. I think it was at the AI days from EASA, where basically on robustness, we describe it as 3 ways to address it. So you have different methods available. These come from the standardization effort we are bringing also in the table. So we have empirical methods, you have statistical methods, and you have formal methods that are on the table. some of them have good properties on some requirements you want to match. Some of them has not so good properties, and we try to see where each one has strengths and where each one has weaknesses. And so, for example, for formal methods, you have different way to do it, but usually you don't get global results. You'll only get local results, which is good in some cases. That's what you want. Statistical methods are usually a combination of different metrics, and you can explore very far away, but you don't have very much, confidence because you cannot prove, you cannot verify everywhere what you want to verify. And empirical methods basically need some human intervention. So you need some insight, you need some brain to tell what kind of stuff you want to test, because you want to design a very specific and narrow test which will stimulate your system in a certain way to verify something. And so there is no one fits them all approach. So basically the answer would be to combine them, to try to multiply the benefits of each one in order to cover as much as ground as you can. So for each of these methods, basically we have different properties we want to test. And some of these properties were explained in the ASI concept papers. So for example, you want to test stability of the training algorithm, you want to test the train model stability, you want to test also the stability of the inference model when it's on the hardware. You want to verify also there is no bias, there is good variance. You want to verify the robustness on corner cases, for example. And we added some more in the first deliverable where we talk about the testing the relevance. So basically, is my system giving me the good answer for the good reasons? And also the reachability. So can my system, when it go on and on, can attain a certain bad state I don't want them to attain. So in this task, in this phase, we focus on mainly three requirements that were described in the ASI concept paper. So basically element 11, 12, and 13. So we're task 3, so we're located more on the right side and on the bottom of the W cycle. So element 11 basically says, I want my training procedure to be stable. So basically, if I have a neural network and I train this neural network on this data set, if I were to change a tiny little bit my data set, I don't want the outcome of my training to be widely different. That seems fair to say. However, from our perspective and first experiment, that seems also difficult to attain. Because basically the people that manufacture the training processes don't really care about stability of their own algorithm. They just want to have something performant at the end. So we anticipate that this might be kind of high risk to verify. It might need some more work to be done. Element 12 is the stability of the trained model. So if I have a trained model and I assess my model on a specific data points, if I were to change a little bit my data point, I don't want my system to go awry. So this seems very fair. And this seems something that most of us have already in mind when we want to test a neural network or a machine learning model. So this should be quite easy to implement because we all think about that. So we should have already tools and procedures to assess that. Finally, LM13 is about kind of the same of LM12, but on very edgy or corner cases on my ODD. So I don't want just to have like a stability on the intended domain, but I want to verify on the edges what can happen, how much my system can take that. And here again, should be kind of easy depending on the ODD. Basically, if my ODD is kind of hard to manipulate or define, I might have trouble to guess what are the edge and the corner of my ODD. So medium risk. It's not as easy as the LM12, but should be doable. So before we jump into the next phases on the real use cases that was presented, we had some toy examples that I'm going to talk about. So here we focus on 3 toy example. The first one comes from the aerospace industry. It's basically a space lander that want to verify that if there is crater or no crater, where it's going to land. So kind of image classifying system, rather small. And on this one, we can test the 3 requirements, 11, 12, and 13. And what we want to test is basically assess all the stability of the training algorithm, the general stability, but also stability against specific perturbation, because you're a space lander. In space, stuff happen, and you want to test what kind of stuff you're going to resist to. Second one is more an image detection, so also YOLO kind of architecture. So it's really public domain. The dimensionality is rather high because this kind of architecture takes place in order to run. And on this one, we just want to verify that some generic stability LM12. The final one, in order to distance ourselves of the classical image processing, is about time series. And so here it's from the healthcare industry. It's heart rhythm anomaly detection. And we want to verify also here stability of the training algorithm and the stability of the train model. So let's delve a little bit more on the first one. So first one, space. You're a space lander. You want to verify whether or not there is a crater on your trajectory to land on something. And here we have pictures that are real, that are from the Rosetta mission. And we work to train a small convolutional neural network in order to tell us whether or not there is a crater on the picture. And working previously also with the European Space Agency, they told us that in space there is this kind of distortion of the picture that occurs by either something called flares, little circles you have here, or gamma radiation going through the sensor. And so these worries them because they say, well, I want my system to resist that because that can happen anytime. And so for them, the ODD was kind of maybe easy to define. When you're in deep space, it's kind of easy, but when you're starting to approach the landing ground, not so easy. So they were able to explain what kind of extreme condition they can have, but they cannot describe what are exactly the condition on the ground, because, well, you have to be there first to know what is on your comet or your asteroid. And usually you've never been there. So you don't exactly know what to expect. So you kind of derived your ODD from previous ones. So kind of difficult to do, but they were managed to do so. So first, we ask ourselves, okay, this is a very basic neural network. It's kind of small, rather easy to train. Like we achieve 95% accuracy rather easily. And then we ask ourselves, okay, training stability. So what we've done is basically we take the data set, we remove one data point, and we retrain the whole model. So obviously we use the same random generator seeds, etc., in order to have like perfect match. And what we can see is that for some weird reasons, sometime the training algorithm outputs something that has nothing to do with the previous accuracy we achieved. So basically on the left, the x-axis is one data point we removed, and the y is the accuracy we achieved. And so most of the time, we are rather in the 95% range. But for some reason, you remove one data point and you lose 20% of accuracy on the same neural network, same database, same validation set. So not sure that the training algorithm is able to guarantee any stability there. Second experiment we've done is, okay, but what if I remove more than 1 point? Let's remove 1%. And so the x-axis there is basically how many percents I'm removing from my training set. And here we have even weirder results, because basically at some point you remove like 10% and you drop from almost perfect accuracy to 0, and you remove more and you go up. You go back to 95%. So basically, you cannot just assess like that if your training algorithm will be stable. Side effect is that when you do this kind of experiment, you ask yourself, well, do we have more data than we need or less than we need? Because if I can remove, like, I don't know, maybe 80% of my data and I still have some good accuracy sometime, do I really need my 100% data? So these can go back to your task 1 and say, is my data representative? I have enough data or maybe too much. Second experiment, still the same neural network. Okay, I have my trained neural network, 95% accuracy. I'm happy with it. Now I want to verify how much it can take variations of the input space. And so I'm considering variation that affects all pixels at once. And so I want to verify how much I can prove using formal methods the stability of decision. So if I were to change every pixel from plus or minus 1, do I have like a same classification as this is a no crater image? And here the results are kind of disappointing, because even for 1 or 2 pixels, most of the time we cannot prove that the system is stable for the dataset. So it means that either there is adversarial examples everywhere in the input space, which is kind of bad, because that means that can occur, or maybe formal methods here have trouble proving that. So we ask ourselves, okay, so how we can go further in order to investigate that? So we went further and we reused the definition of the perturbation they were telling us about. And we say, okay, let's try to prove, same scenario, proving with formal methods, how much my system can take on really weird specific perturbation. So flares and radiation. So the first step you have to do is have a mathematical description of these phenomena. And so it's kind of easy because it's pictures, so you can have like a mathematical model that encompass this kind of perturbation, so straight or circles. So kind of easy. You can do that. It seems doable. Maybe on some different perturbation you might have trouble, but on this one that was feasible. And so here we do the same scenario. We test on this kind of perturbation and we want to verify how much the system can take in. So first, flares. So here, what we discover is that we can prove much more stability on this kind of perturbation than the general one that affects all pixels. So for example, here, we managed to discover that, for example, for variation affecting pixels on the flare at plus or minus 10 in intensity of the pixels, we can have like half of the pictures that are still stable. So that's still better than before. But what we discover also is that suddenly we had different behavior between pictures that have crater or no crater. So basically crater image were much more stable than non-crater image, which we didn't see before because on the statistical analysis on the validation sets, both were 95%. Like from the point of view of the statistical analysis, everything was perfect for both classes. But now when I'm doing stability analysis with formal, I discover that one class is way more stable than the other. So that might bring also knowledge to my data sets, to my training set, and say, hey, maybe I have trouble in discovering these images, or maybe I have imbalance somewhere that I should look on. On radiation, we even achieve stability on crater images for variation going from minus 255 to plus 255. So basically anything you want between black pixel to a white pixel. So here you cannot do much more than that. So basically we can prove that if you have like a straight line somewhere, your system will not change decision as long as it's a crater image. Otherwise, if it's non-crater, you can see that these curves tank rather sooner. So it's way better than the previous results we had. Like we cannot achieve more than plus or minus 1 or plus or minus 2 in pixel intensity. Here we can achieve like basically the maximum level. So this gives us hope that we can achieve some results using combination of formal and statistical in order to place some perturbation, different at different locations and also at different intensity and verify all of that. Second use case. So we try to see whether or not we can process the YOLO architecture at some point. So at this time, it was quite a smaller one, like YOLO v3. So basically, each version like doubles in size. So we stayed at the v3 at this point, and we tried to verify whether or not it's feasible to use formal methods on that. So I never heard before this kind of result published because usually formal methods in the academian sector limits themselves to very small neural networks. So here we are up to dozens of millions of parameters and not just like a few neurons. No. So the results are basically that it's still hard. It's feasible, but if you have time, basically, it doesn't take seconds. It's more likely you're gonna take dozens of minutes. So still work to do there, but we managed to prove that it was feasible to measure stability, for example, on one box, considering a perturbation around this box and inside this box. And we managed also to extract some relevance. So basically, we were able to explain why the system is telling me that this is a person using formal methods. Problem is, when you want to move to LM13 and do some corner cases, well, you need to have your ORDD set up. And then it's painful because driving on the road in France is not an easy ODD to set up. So we didn't obviously have time to set this ODD up. But if you were to have a slightly less difficult ODD, like my plane is on the air, I might be able to define a better ODD which is feasible to explore on the LM13. Finally, we have the time series classification. So here we have a database, a public database containing more than 800,000 heart rhythm. And we have 5 classes telling us that it's a normal or some form of abnormal heart disease that you have. So the ODD, if you are an expert, kind of easy to define. However, the abnormal cases are very hard because each individual can have a different abnormal heart disease. So it's not easy to say what is abnormal and to describe it. You can just say it's not like the normal one. So it's easy to define normal, but not the abnormal. We have time series that are quite long. We have almost 200 instant to process each time. And we managed to process that with an architecture we found on a paper, which is basically some convolutional neural network. So it's not a tiny neural network, but it's not a quite weird one. So here again, first, can I have training stability? And the answer this time is more yes. Because we picked one point out on the left, and we never see a change more than 1+ % in accuracy. So if you were to only look to this use case, you would say, well, training as stability is feasible. So it depends on the use case, apparently. Sometimes you can have training stability, sometimes you don't. We use exactly the same training algorithm, basically Keras. So we didn't change that. On the other side, when we remove more than 1 point, like 1%, 2%, etc., we kind of have expected results. Like at the beginning, you remove data points, it shouldn't, break your system. But if you remove too much of them, at some point it should break. And that's what happened when you reach like 90% of your your training set. Then suddenly your system doesn't work anymore. Well, your training doesn't really work anymore. So here again, I probably have way too much data to train on, since I can remove like 80% of that and still have like 95% accuracy. So that should also give us some hints about whether or not how much data we need, depending on the difficulty of the problem we want to address. It still doesn't explain why I can go up when I remove, again, too much data. This we don't have an answer yet. We're still investigating, because it seems weird to remove more data and have better results. When your systems start to break, it should break all the time. Then we want to assess, okay, so I want to verify stability in a general sense. So if I were to be a classical AI engineer, first thing I do a confusion matrix, and I want to have like my nice diagonal telling me like everything is 95%, and normally I should be fine. We did that, and then we ask ourselves, okay, we have like a pretty good diagonal there, except on one line. So one line, it seems that on this particular class, the accuracy is slightly less than the rest. And so we ask ourselves, okay, but does this mean that it's less stable? And so what we've done is that we do the stability analysis on each class separately, and wanted to see whether or not this particular class breaks before the others. And the answer is yes. The answer is yes, because at a certain thresholds, basically all of the other classes are still fine, green, and it doesn't change classification, except this particular class where we have like less accuracy. So it seems that there is still a link to be made, and maybe published, that if you're not very good in accuracy, you shouldn't be very good also in stability. But that's full empirical yet. We don't have like mathematical, and theorem on that. It's just an intuition we have. So finally, some takeaway we had during all of these experiments. First, when you do these formal methods and you want to see at which point the system can break, basically what you do is class separation. So you measure at which point the system can change decision, and looking at what decision you can jump from one another can give you hints about the vulnerabilities of your training. Because if you know that your system can confuse this class with this one but not the other, then you have a new knowledge to take inside your dataset, and maybe say, well, what can I do to differentiate more of these two classes? Second part, when you use specific perturbation, you basically learn more about the weaknesses also of your system. And it's really important that the ODD you define is including all of these new perturbation you want to test against, because then you can measure on which one you have to get better, and maybe train more. Data augmentation, synthetic data, you name it, you can find new ways to augment your robustness on that. I didn't talk much about the relevance, but when you analyze why your system is taking a decision, and if it's for the right or wrong reasons, you can detect bias in your system. And so from there, also retrain, remodify your training data in order to include this knowledge. Finally, one side effect we discover on the time series experiment is that at some point we had some very bad stability on some data points, and we find it really weird that why these data points have a tanking stability, because they were accurately being classified, like it was perfect, like 95%. But when you modify the stability on them, it doesn't take any modification. And the reason for that is because they were all wrong annotation. So by measuring stability, we discover in the training set that we found online and that was published, like there was a huge part that was clearly not well annotated. So we can imagine that from the end of the process, when you are assessing stability and robustness, you can go back to the first square where you're in task one and verify whether or not your system, your training set is well qualified and well annotated. So you can see there is an interplay all the time between the different tasks you're going to run and the way to improve your system overall. And with that, I think we can move on to the Q&A session.
Thank you, Arnaud, and thank you all for for those great presentation on the progress on the three tasks. Sorry. So we have 10 minutes for the Q&A session, and then we will take a 10 minutes coffee break. So is there any questions for those who are in the room? Yes. Where is the microphone? Is just over there. Thank you.
Okay, thanks. Dimitri Collins, Collins Aerospace Applied Research and Technology. So I have a question to Arnaud. Thanks for presenting all this. Very, very interesting. I have a question about stability. So when you were removing points in your analysis, have you always tested on, have the test data set been frozen, and have you observed any correlations between the points you removed and where the performance went down with respect to the test data?
So you mean for training stability?
Yeah.
So basically, we take the training set. I should have said, when I remove 1 point, I remove 1 point from each class in order to keep it, balanced all the time. So kind of misleading you there, but it's not like we remove like billions of points. And we always validate on the isolate different data set which doesn't change. Does that answer your question?
But for example, you remove a point with a bicycle, I don't know, from the training data set. Have you seen any correlation on where the performance went down in the test data? Is it on the bicycles or is it random? So is there any correlation between the points you take away from the data and
right? Okay, so you mean by class? So yeah, we run this experiment. I didn't have this on the slide. From my memory, we had like similar results when you look at only one class at a time, the accuracy on one class rather than the others. And so no, it wasn't correlated to one class in particular. You observe the same weird, anomalies in terms of behavior, whatever the class you were looking at specifically.
Yeah, thanks. A related question, if I may. So, stability analysis is about removing points, but maybe a concern about data poisoning. So, in cybersecurity, right? When data poisoning is when you add the points or when you modify the points. So, do you think this should be part of your of the analysis on algorithm stability?
Cybersecurity, I don't think I think it's covered by different requirements. I think the LM11, which is training stability, doesn't really talk about cybersecurity, but it's a quite good question. I never thought of it. I might defer the answer to the next to the next event in May.
All right. Yeah. Thank you. Thanks.
Thank you. Yeah, there is a question over there.
Thank you. Raul Giazon from Airbus Protect. So the question that I have is, so relating to the stability, have you looked at if you change the training algorithm and do the same removal of data, how is it impacting the model afterwards?
Not yet. We still use like the Keras, but yeah, it shouldn't be too hard to do as an experiment. My intuition is that they will all have the same behavior, because from my experience, none of the manufacturers of these training algorithm has the stability in mind. They basically don't care about that. What they want is a performant model at the end and the fastest way to get there. So they don't really care about of this problem here. So if by chance one of them has an implementation that does that, it will be by chance. But you're right. We should do this experiment at some point.
I think the underlying question is also whether it's about the data set that you're removing, right? Whether it's adding a specific type of information that's missing from the rest of the data set, right? So if you're changing the training algorithm and then they all behave the same in a sense, maybe it says something on the training set, right?
Oh yeah, you can. Oh yeah, you say that. Okay, I have one data set, one neural network, blank neural network. I'm testing if every training procedure should output something widely the same. Not sure that can really work because there is like a lot of random beginning at the beginning. I'm not sure we can make sure the conversions of each of one. That's a good question. I never tested. I'm quite pessimistic that would work. Sorry.
Thank you.
The question can be for all panel. It's not just on task 3. Yeah, I don't have a chair.
So Samira Lau from the Uni Stuttgart. So I have a question. So very nice, the different results. I was wondering if you have worked together. Because, for example, when you talk about the stability and you take the data, point data, it will be also interesting to see how that affects the representative and then understand, okay, how that actually can help each other, because there are different parts of the development and that actually can feedback to each other. So I was wondering if have you worked together or understand how your work, for example, is tied to the rest.
You want to take this one?
Yes, thank you for your question.
Yeah.
Yes. Okay. Thank you. So concerning the work all together with the different tasks, yes, we are currently, in fact, having some the conclusions that have been already shared between the different task holders. We are fortunately having same directions concerning the impact of some parts concerning the ODD, the data impact, the impact of the model configuration, etc. And on the next phase, we will have for at least 2 different use cases, implement the generic end-to-end pipeline that will be presented just after the coffee break, where we will evaluate at the same use case, the impact of the data practices, the model training and the generalization limitations, but also the impact on the stability and the robustness. So having that pipeline end-to-end evaluated will bring more questions, open questions, but also will bring a lot of solutions, a lot of recommendation on how to enhance the complete pipeline, but only the data part, the model or the robustness.
Yeah, Gary, one more question.
Okay, thanks. Just to be fair, I would like to ask on stage 2, so we can. So what's the question for you? So what I seen was a lot of attempts to look at the objectives in yours, and you pointed out LMO4, LMO9, and the safety. What I didn't see, and I hope to see by May, is actually LMO4 says quantification, generalization, and I'll ignore the last word because it doesn't exist, okay, for me. So by May, will you be able to answer the key question, which is out there, which is of a significant need for the working group on SAE G34, use case 2 relevant, FAA are aware of it. I spoke yesterday in a technical meeting, and EASA is certainly aware of it. So by May, I'd like to know whether you can answer that question, because what I heard at the beginning was we're here to look at the objectives. So that objective is clear. What I haven't seen is that up here, the quantification, you didn't do anything about it. You just said, oh, we need to bound it. It's very difficult. Lots and lots of uncertainties. So by May, I'd like to know how many uncertainties remain and how many certainties are achieved. Thank you. Can you answer that for me?
No. And the objective was clearly to test the means of compliance. So there is an objective to quantify this generalization. We test some objectives to try to quantify, or at least to give some bounds to say, with that level of confidence, I can guarantee that, or I can ensure that the level of generalization, which is, again, the generalization, is the average error I'm doing on the full domain. It doesn't mean that for a given input, I have an attached certain uncertainty. So my point is that no, I will not be able to provide to you, at least we identify some alternative and we need to test them. But up to now, I don't see how I can quantify clearly the generalization with an acceptable level of confidence.
Perfect answer. I can't believe your answer. It's so perfect because you point out level of confidence. This is what I explained to the FAA yesterday in a technical meeting. It's about, at the end of the day, having a level of confidence. You say you can't do it for me. I believe we can't do it at all. But this is what I'm trying to get across. And your answer was exactly what I would have said. And I recommend, I really appreciate that answer because it was perfect.
But in parallel, I fully understand the objective put by in the concept paper. We need to demonstrate something. Can we do that?
But that, to me, can be bounded around a level of confidence, coming with a combination of evidence, be it Bayesian safety validation or whichever, which is out there, performance metrics, percentages, error rate, understanding, threshold, is it inside the threshold, the error rate, then it's acceptable for safety. If it goes outside the error rate, outside that threshold, does it become a false negative because we can't detect it, or does it become a true positive because we actually do detect it? So for me, it's very much a qualitative combinational of evidence supported by quantification like performance metrics, percentages, and error rate percentages. And also it can be some probabilities, but it doesn't have a probability that can be translated into a failure rate per flight hour.
So if I might add an important detail, it is in fact about the understanding and the interpretation that we will asset to the quantification aspect. It means that we will need, in fact, too many elements that you said. You have mentioned the error rate, the acceptability, the uncertainty quantification, and also too many criteria related to the performance of the AI that will not harm the safety critical systems. And how we can quantify all those elements, those features, limitate the impact on the safety, and provide a way, in fact, to do that in a better way. It is not about one magical formula that could quantify the generalization and give that guarantee. I think it is about the interpretation that we can asset, in fact, for this aspect. And too many elements need to be quantified and combined in order to say that we are guaranteeing that the AI will be behaving in a good way on the target system.
Okay, so it's combinational as I expect, but rather than the guarantee, it's a level of confidence, combinational level of confidence of evidence. So it's a product and a process, and the process that we want to do by objectives through the ARP 6983, ED 324, as with the EASA concept paper, is trying to ensure a level of confidence of the product when it's deployed in the aircraft, and the safety risk mitigations where necessary, proportional to the reliance. So I think we're all heading in the right direction. It's just that we have a little bit of a impasse situation. Okay, thank you.
So we have one more question. So it's about ODD. So what ODD are you referring to? So formal ODD, training and data-based ODD, or both? So the question is about ODD. So which one are you referring to? So is it the former one, the training database one, or both of them?
I would say it's any of them, depending on how you formulate your problem. We don't have a precise how to say that. We are not precise on the ODD. The notion of ODD, whatever it is sufficient for us. Any in a sense, any specification document will provide upstream information for the design, the design of the method for the assessment of completeness and representativeness. It will drive the assessment. So I hope it answers the question.
Thank you. So we have one more question, and then we'll have a 10-minute break. So the second question is: have you? Sorry. So go ahead for your question.
Hello, it's Muhammad Hon from Capgemini. My question actually concerning the data set for visual inspection, how it was generated, or it is synthetic data set, or it is original realistic one.
This is a real data set. it is a collected data set by a specific project on Airbus, where the objective is to help the operators detect the damages and help the prioritization maybe of the maintenance operations in a better way. So these are real photos collected from the project. Yeah.
Was it enough for the training?
Sorry?
Was it enough?
In fact, it wasn't enough. That's why we have mentioned some possibilities to consider data augmentation, or maybe also check for other open data sets, because we have found several open data sets for cars visual inspection, but for the aeronautics there is a lot of, in fact, confidentiality, and people are not happy sharing these kind of data sets. Yeah.
And this the task of visual inspection is just external visual inspection, or also for the motors, etc.
Currently, it's only focusing on the external damage detection for the fuselage of the airplane. In fact.
Okay. Thank you.
Okay, so one more question. So, have you modeled the computational cost for formal method application? So the question came because often we spoke about scalability with that math on it.
So the short answer is no, because it's quite hard. You can have like an estimate, a pessimistic estimate, that tells you will need like a terabyte, but in practice, usually you don't use that much. So the difficulty is that the kind of formal methods we use is called abstract interpretation, and basically when you're dealing with non-linear functions, sometimes your abstraction, your formal approximation of that needs to get a little bit bigger in order to take this non-linearity in. And depending on the model, depending on the size of the input domain you want to validate, your abstraction is going to get more large or not large. So it's context dependent, it's use case dependent, it's data dependent, and it's also dependent on how much you want to validate in at the beginning. So it's not easy to just say, yeah, it's quadratic or it's cubic, or it's like it's not like an easy algorithmic complexity you can express. So sorry for the non-answer on that.
So let's carry on with the presentation. So floor is back to you, Tizeri, with the presentation of the generic end-to-end artificial intelligence development pipeline proposal and the joint conclusion.
Okay. So thanks again. Hi, everyone, for a second time. Now that we have seen the different technical results, the experimental results on the data analysis, the qualification of the data, the impact of the data on the generalization and the robustness, and some specific characteristics of the model, let's put all these findings together and identify the most influencing elements. So the main purpose of this part is first to identify the common practices, in fact, that are used in general data science when we develop AI. These common practices that we call, in fact, the common pitfalls that harm the model and prevent, in fact, several AI projects from seeing the light. So why? Because, in fact, for some reason, there is too many common practices that increase the gap between the experimental analysis and the experimental objectives, the evaluation, and the industrial qualification, the industrial, in fact, point of view of what is a good model. And at this stage, we would like to put all the conclusions together, and also based on the empirical analysis, what is the best, in fact, to do. let's say, in the more optimistic way, in order to help the development of AI-based safety-related systems and help the implementation of the W-shaped learning process for different projects. Starting from the identification of these key pitfalls and providing on the second time ways to overcome these different limitations, and then finally put all together and complete the generic pipeline where we will describe each step in more details. So let's start from the identification of the different elements that at the different stages of the W-shaped learning process. Here we focus on these learning assurance on this W-shaped for the AI development, because it is the purpose of the project. And through the journey of developing the AI, at every level, at every step of the complete process, we have identified a wider list. Excuse me, so it doesn't support my hand, so I'm not going to touch it again. So, as I said, we have identified the most elements that could impact the result, starting from the system level. So here we refer to the incomplete ODD, which means that from the system level perspective, if we haven't a clearer and a more completed ODD definition, the operational design domain for the AI component, which highly influence, in fact, the AI constituent requirements, we will be misleading, and the remaining of the steps will not be completed successfully. Where, for example, at the AI constituent on the data management, if we don't have a completed ODD, we could have some missing elements on the data quality, and the completeness and representativeness could not be assessed in a good manner, such as, in fact, the presence of some specific cases, and also the handling of the outliers and the edge cases, too many elements related to the data, how we can take into account all these elements. If there is some problem into the data qualification and also the assessment of the sufficiency of the data to train a model, but also before going into the training, identification of the complexity of the model. If I don't have enough data to make any AI or any let's say equipment rather than the human perform the task and complete the task correctly, there will be a problem. And the problem on the data will have a huge impact into the learning management, the verification, and the evaluation of the model. At this stage, there is a very wide list of, unfortunately, too many elements that could impact the model in terms of generalization, but also the robustness and the stability of the performance. If we have an overfitting or underfitting model, it is very clear that the underfitting and overfitting is not good to the model, and we will not have the generalization or maybe the required performance of the model. But there is also too many elements related to the definition of the training objective, the choice of the metrics, the evaluation metrics, and the understanding of the KPIs, the key performance indicators, from the industrial point of view. What is, in fact, from the point of view of the expert, the good black box that could make the job correctly. Understanding this objective, it means that we will be able to select in a correct way the metrics if there is not the metrics on the literature that could assess correctly this industrial objective, we need to think it again, and we need maybe to provide a new metrics or new learning objectives. So be careful with the objectives, that the learning objectives that you are selecting from the literature. And finally, if the model is not generalizing, or if there is some problem in the learning verification, it means that the model will have also a problem in terms of robustness and stability of performance. As already presented by my colleagues, there is a very impact of the data into the model performance, but also into the stability of the results. Sometimes we cannot, in fact, identify the impact of just removing one sample from the data, why the model is behaving this way. We need to go back into the design of the model, into the data qualification, and verify the different impacts. So we are not raising questions. Let's provide some specific answers. For the data management, so we suggest to drive the data management based on two key points. So the first one, as said by my colleagues, is the ODD as a centerpiece of the data quality. And the completeness and representativeness should be assessed according to the ODD, which is very framed, in fact. I cannot assess the completeness and representativeness for the AVI use case for any kind of image to detect for example, a damage on the skin of the airplane without saying that my model should see the images taken outside at that intensity of the light, etc. I need to frame it correctly. And then the second element is that the necessity of taking into account the model behavior during the training, the evaluation, but also while assessing the robustness and the stability of the model. Taking out some data points and seeing that there is a big impact into the model behavior, it means that there is some problem into the data. That's why we need to go back into the data qualification and see what is wrong, in fact, on the data, in order to see how we can leverage the model feedback, or in terms of generalization problems, limitations, but also the limitations concerning the robustness, etc. We need to take into account all these as a feedback to enhance the data. For a second part, concerning the model training and the generalization and the assurance that the model will work correctly on the target system, there is also a big list of verifications that we may need to perform to drive the model development and training, because it is not only the magic of data, it is also the logic of providing an architecture of a model that is more accurate with the ODD. That's why we need to rely into the ODD analysis outcomes. So knowing the data type, the volume of data, the system level requirements in terms of what could be accepted as model architecture, is the model expected to run in real time, what is the maximum of performance, but also in terms of influencing elements from the ODD, the already known characteristics of the target application, of the target context, of the target deployment system that could have a significant impact into the data, into the model performance. The second element is to focus on the target performance objectives underlying the industrial objectives, because the bigger problem is that we have a huge state-of-the-art for every industrial concern that we have today, and for which we would like to use an AI. There will be always something already done, something already proposed in the literature, but it is not, in fact, a well-prepared cake that we can take and use and consume directly. It is not like this. We need to align the objectives between the evaluation, which means the selection of the metrics that could be correlated better to the KPIs, but also the selection of, for example, the generalization assessment, the bounds, and taking into account also the critical system requirements, where there should be no impact on the safety. So this is, in fact, our colleagues from the safety are very, in fact, let's say, exigent, if I can say, concerning the performance of the AI. And this is true because we cannot accept that adding a new model will impact significantly the safety. So we need to be careful while developing the model, starting from the ODD, the alignment of the objectives, but also providing ways in order to enhance the performance of the model by detecting what are the most impacting elements and how we can overcome the different limitations. And then finally, we need to reinforce also the model robustness and stability. As presented in task 3, there is key elements that we can integrate, in fact, to boost the stability. Before giving feedback to the ODD preparation or to the data qualification and preprocessing, we can at least analyze, for example, what is the minimal perturbation that can change the model performance, and what can make the model make more mistakes. So there is more than these as recommendations to enhance the complete pipeline. So as I said, we have put all these recommendations together at the different stages of the generic pipeline. This generic pipeline, as I said, it represents an implementation of the W-shaped learning process, where the objective is first help, in fact, the different AI operators providing AI-based technologies while minimizing, in fact, the risk of not being accepted by the regulation, for example, answering the different means of compliance for the verification of AI, but also minimizing as possible the impact on the safety of the target system. So this complete pipeline is presented in 3 big parts. The first one relates to the target application definition, including the ODD specification. The second big part is the core of the design, development, and validation into the implementation of the model. And finally, we add some recommendations and some key points to take into account while deploying the model and how this model can be taken into the monitoring. Starting from the target application definition, as I said, it is built around the understanding of the objectives of the ODD, but also the system level requirements. The system level requirements will drive the AI constituent level requirements in terms of starting from the data sets, qualification, and the performances, the influencing element detection and listing, in order to have all the required input information to go into the complete pipeline of developing the AI, having in mind all the required elements concerning also the performance measures, but also all the knowledge that we can have concerning the target system, the target application, what are the requirements, what are the error margins that can be accepted, etc. Then, going into the big part of the pipeline, this one is made of 2 stages of evaluation, where in the a priori evaluation, here we would assess all the inputs that we have already collected from the ODD, the inputs in terms of knowing the target application, the target system requirements, but also all the, let's say, maybe the generalization bounds that we have selected, the metrics, how we would evaluate the model, etc. Having enough data for the model that I would like to implement. For some reasons, we can have less data, but on the data qualification, we need, in fact, to anticipate means to have more data through the augmentation if needed, or maybe using other kind of data. And then in the second part, the second step, for the model design and adaptation, here we need to have as input the data qualification elements, so all the outputs from the data qualification. Because if in my mind, for example, for some use case, I want to use, let's say, the LLM's model, so this is the well-known technology nowadays, but from the data point of view, I know that I really don't have enough data. So at the output of the first loop, there is too many restrictions for several technologies. But if I cannot satisfy the required inputs through the loop one, but also based on the ODD definition, there is also too many requirements that I need to take into account while designing the model. As I said, minimizing the impact on the safety, having more space, storage space, for example, or more characteristics of the infrastructure that where the model will be deployed. There is all these elements that we need to take into account during the design. And moving into the model development, training, and the posteriori evaluation, here we will evaluate the first, let's say, on the first pass, the version of the model that has been validated, and then see if this model at this stage can meet the objectives of the target application. I repeat again, the benchmarking including the industrial KPIs. So it's good to have too many evaluation metrics, but we need to stay the closer as possible to the expert of the domain in order to see if the different interpretation that I, as a data scientist, can associate to the different values, the outcomes of these measures, if this interpretation can meet the objectives of the expert, we are at somehow aligned, so we can go further. But if there is still a gap between the requirements of the expert of the system and my requirements in concerning the performance of the model, we need to redefine something. We need maybe to redefine the measures or combine too many measures in order to evaluate the model correctly. And then go into, after this evaluation validated, so we can go into the model implementation if it's okay. But if it's not okay, if I'm not aligned with the expert and with the requirements of the target system, we will need to get a step back. But where? We need to get a step back to the data qualification in order to provide a feedback about the model behavior, where the model is good and where the model is having more limitation in terms of performance, what are the more impacting, the most impacting data points. For example, after assessing the stability, if there is some specific data samples that are having more impact on the learning of the model and the verification of the performance of the model, we can check with the data experts how we can enhance the data in order to go again into the model design, check if all what have been already validated is okay, or maybe perform some additional model setting or change on the design, and then go so on. So we will be at this iterative process until the validation of the model, the evaluation is very aligned with the KPI and the industrial objective. And then go into the implementation, but it's not finished. It's not finished because this is the moment of truth. So I call it like this because after the implementation, this is where most of AI models fall, because changing the technology, changing the running context, the running environment, all these elements are very impacting the AI behavior, and we can see a significant drop in performance. So there will be always a drop in performance. So you need to check with the expert, with the industrial objectives, if this drop in performance is not highly impacting the acceptance of this AI, if there is not a big impact into the safety also, if all the what has been already verified in terms of generalization, the combination, the quantification of the quality of the AI, of the performance, of all these elements have been accepted by the expert or by the industrial point of view, you can go into the deployment. But if this is not the case, you can go some steps back, and going some steps back from the implementation, it means that all what you have already done needs to be revised, including the data qualification. Why? Because going from the implementation into the model design, it means that you are redefining a new model, but in order to redefine a new model, you need to take into account where the model has failed the most after the implementation in order to make it better. And then, since the model has been accepted, you can deploy it. And after the deployment, so in the monitoring of the model, while you are using the model, there is also too many things to bear in mind. So when you use the model, you have been validated through all this pipeline. So going into the model in the target system, it means that you will have a model interacting with the real system. There should be, at the monitoring level of the system, so above the AI constituent level, there should be a way, in fact, to identify where the model is making errors, for example. So this is not at the scope of the MLEAP project, but we are making this recommendation because it is very important. Working in another parallel project related to safety in AI, we are in fact analyzing what should be taken into account at the monitoring level of the AI in order to have less impact into the safety. It is not on the scope of MLEAP, but we need to take into account this element. And after the model has been deployed into the target system, it could happen that we will have some changes at the system level. So the whole system is getting updates. So we have some objectives evolution. Today we are just assessing images, and tomorrow maybe we would like to include a voice analysis, etc. It means that we need to go back into the ODD definition and recompile the complete pipeline. It doesn't mean that the model that has been validated and deployed for the system at time t0 will behave correctly for a new system having new requirements, new objectives at time t+1, for example. So that's why we need to go back into the ODD and recompile the complete pipeline. It can mean that the same model that has been already validated can be reused if this is possible. If it is, for example, just a data evolution, so you can retrain the model, fine-tune it, for example, to add some new features to take into account the new data samples that will be added on the data that the model will see on the real life. But you need to verify again all the things that I have just explained concerning the evaluation, meeting both the industrial and experimental objectives, the learning process, etc. You need to verify again all the things while using the new model, or maybe redefining a new model, because the model that has been already validated cannot just be included in the new system. I think I have already explained all this. Let's get into the main conclusions. Sorry. So the first main conclusion, and which is common for the different 3 tasks concerning the data qualification, the robustness, stability, and generalization, it is that for every machine learning and deep learning development, the key point is to ensure a complete ODD in terms of, so it's not a complete 100%, but a clear ODD that will condition, in fact, the data quality verification, the data volume assessment, but also it will condition the model performance because you will be training the model on the verified data according to some ODD. And also, depending on the use case criteria, for the data verification and qualification, the model learning verification, and the robustness, etc. The common conclusion that we had through the different experiments is that there is no one fits all. You have, in fact, to combine several methods in order to reflect all the performance that you are targeting, including the different performances features related to the model, but also all the different quality criteria related to the data. And at different stages of the W-shaped learning process, in a correlation with the pipeline, we have identified several common practices that are, in fact, common mistakes that can lead the, let's say, the experimental objective be far away from the industrial objective. And at least three main elements to take into account for a secure enough machine learning development. So we need to understand to have a good understanding of the ODD and the target application characteristics, the data type, if there is several specific cases that we need to take into account, etc. And then consider, as I said, the system level requirements. In terms, again, of safety-related characteristics, it means that what is the maximum amount of error that the target system can leverage and, can accept, and if there is at some point at the monitoring layer of the system, if there is some functions or some possibilities to detect the errors of the model or to overcome them. And again, you have to check with the expert. So we are AI experts, but we are not experts of all the domains. We need, in fact, to check with the target system what needs to be verified and minimized or maximized. And again, before moving forward, you need to make sure that there is no risk or less risk, in fact, from throwing the model by the target system, because you need to test, verify, evaluate, and perform a more rigorous error analysis in order to identify where the model is making a mistake. Even if I have a 99% accuracy, it doesn't mean that the model will be accepted and will have zero risk for the safety. It means that I need to quantify too many criteria related to the model quality, to the model performance, in terms that the objective of the generalizability, the robustness, the stability, all these elements need to be, in fact, quantified in terms of sub-criteria, and how the whole, in fact, the whole quantified elements can be interpreted by the target system, and how the behavior of the AI can be bared by the target system. And finally, let me remember that here the objective is, as I said, to provide a way, in fact, to implement the W-shaped learning process while you are developing your AI for safety critical systems in aeronautics. And at each stage, we provided the common mistakes and to be avoided, and how you can overcome the different problems, and in order to help the certification of the different AI that you are providing. So that's all for me. We can go to the Q&A session.
Thank you, Desiree, for this presentation. So let's take some questions. I don't see any questions on the BlueJean interface, but is there any questions directly here? The microphone is here.
Thank you, Desiree. So actually, I have two questions, but they are connected. First, I would like to clarify the concept of generalization bounds.
Yeah.
Because, so I am from systems, so from my perspective, I allocate a requirement to the model or the constituent, which is a performance requirement with thresholds and boundaries. And therefore, I say if I design my architecture and my system so that if my model meets these requirements, I basically should be okay. So the first question is the generalization bounds. Are they the same bounds as this requirement that I'm going to allocate to the ML constituent, or are we talking about something else? And the reason why I'm asking this is when you say no safety impact. This is where I have the linkage, because if statistically I say I provide a requirement for this performance over a 95%, I kind of agree that the last 5%, I don't want this 5% to have an impact on the safety of the aircraft. So I will manage this 5%. So is the generalization bounds is therefore related to this capacity to meet over the statistical requirement of my performance, or is it something else? And did I interpret it well when you say no safety impact?
Okay. So thank you for your question. I will have two answers related. So the first answer is a clarification about generalization bounds. Generalization bounds are statistical tools, are functions that, based on the data characteristics or the model characteristics or a combination of both of them, will give you a statistical value on the capacity of your future model after training, its capacity to generalize. So you can, for most of the functions, as presented by Jean-Baptiste, in fact, for several methods, you can compute this statistical value before going into the training and the development of your model. You are just providing the characteristics of the model, maybe the number of layers, the number of trainable parameters, and also several characteristics of the data, the number of classes, the volume, etc. And then you will compute this statistical value that will be related to the model capacity to generalize, okay, after training. So I said that this is not enough. It is obvious, in fact, it is not enough to guarantee the generalization. We need, in fact, to combine several other criteria that are quantifiable, such as the error margins, the several metrics. But it's not only about the existing metrics, the existing error margins on the literature. That's why we are focusing on the boundaries between the industrial objective and the experimental objective. Because from the experimental point of view, I would say, so I don't need to reinvent the rule. So I have too many features, too many functions on the literature. I can keep them all in order to evaluate my model. This will be enough. But unfortunately, even if you will keep 100 of methods to evaluate your model, it could be not enough to represent the industrial objective. As an example, if you have a good accuracy, but your model is making only one mistake, but in the most critical case, this is the risk and the impact on safety. And this is a specific, in fact, industrial objective where you need to reinvent maybe the metric to evaluate your model by adding the benchmarking. It means that the acceptance criteria, how you can define this acceptance criteria, the threshold, the specific cases, etc. And all these elements are quantifiable. So that's why we need, in fact, to give maybe another understanding of the quantifiable generalization elements. It doesn't mean one only magical function, but there is too many elements that are quantifiable.
So just to allow me to rephrase, and one thing that I want to concur with is that the statistical analysis does not provide you any elements, from my personal opinion, because as you said it, if the lack of performance of your model, which is not the generalization bound, I understood that. If this lack of performance occurs in an area of your ODD where you actually operate regularly, you are in a very bad situation from a safety perspective. So the statistical argument, I see it, and the generalization bounds, I see it as one possible way, but not probably providing you enough evidences to sustain an argument from a safety. And your position today is to say you can use it, knowing the limitations of this method, as part of your process of
the development.
But in any case, and I want to go back to my second question, I believe that whenever I have this statistical characterization, I still have the duty to make sure that whenever I am not within my requirements, it doesn't have a safety impact from an aircraft point of view.
Yes. Yes, we need in fact to make this this verification.
So it means...
So as I said, so the safety analysis, the safety requirements is not at the scope of MLEAP, but since we are working in parallel in another project which is dealing with safety-related analysis for AI-based systems, and we are having too many recommendations still to give, in fact, for the AI implementation. And that's why we have so far added some recommendation for the deployment of the model and before going into implementation, what we can verify in terms of safety. Other question?
Thank you again. There is a question.
Thank you. I would like to come back on the ODD.
Yes.
Because you put quite a lot of stress of focus on it. And in high dimension, it's still a challenge. At system level, it will be defined at very high level features, night, day, cloudy. But for the model, what is important is the actual distribution in the image, for instance, if we do computer vision. So there is a necessary condition that this distribution with the features that you describe, you have a good representation, but it's not sufficient because there is variability in the input space that you will never see with the high-level features. So for me, you need to add monitoring to check that the model is executed in areas where it has been well trained. So having let's say, everything on top of the model and all the requirements or at the model level for safety, for me it's a bit tricky because there are plenty of stuff that we'll add on top to ensure that at least we control where the model will be safely used, and we have to do something when we are out of this region. But having just a view at the ODD and control the ODD at a very high level, because in high dimension it's difficult to do something else, I think it's not enough. We need also to add some monitoring to make sure that, okay, it's necessary to have a good coverage at the high level, but also with the distribution at the image or at the high dimensional space, we are also well protected.
Yes, for sure. So thank you for your compliment. I think you have explained it better than me, but we are aligned, in fact, in terms of the requirements of having a clear ODD. So what I said, it doesn't mean that we need to have a complete ODD. This is impossible for, like you said, high-dimensional use cases, like the different use cases that we have selected in terms of AVI and the speech-to-text. This is a very big ODD, in fact, to have. And also on the other, such as automatic driving, it is a very big ODD to define. But when the ODD is framed, it means that at this ODD, this is what I need as requirements for the data quality. So based on the already defined ODD, so this ODD, it is not us as AI experts that will define it, but this can be defined by the expert because it knows where the AI will operate, and if they have some monitoring layer where the elements that will be missed by the AI can be detected and let's say built by the monitoring layer of the model, so of the whole system.
Yeah, but it's the monitoring is an AI problem. It's not a domain level problem, because it's mathematically that you will define that you are in the right distribution compared to your training. It's not at domain level that you can do that. So it's part of the things that the AI developers have to also provide on top of their model. It's not something that can be done.
So the monitoring of AI, you mean, or the monitoring of the system? So when I say the monitoring, I point to the monitoring of the system, in fact. The monitoring layer of the system.
Well, it can be at all level, but
yes,
but I think there is also a monitoring at the high level, and it's I'm not sure that in your pipeline it's part of it, because it's really focused on really the model and only the model. But maybe, but that's.
So when I talk about the monitoring, so at the latest stage on the deployment and monitoring, it means that here I'm at the system level. I'm no longer at the AI constituent level. So here the monitoring refers to the system level monitoring. So how the system can bear the outputs of the AI. And at this stage, there will be some evolution at the objectives and then go back into the ODD.
Okay. So just one more minute for the question, and then we will continue with the end of the presentation. Yes, you can go ahead.
I wanted to react on Giant's comment. My impression is that there is two types of monitoring. The first one is a real time. I want to make sure that I detect when the performance is not within the requirements I was mentioning earlier, and I need to react. I will not monitor the drift on the distribution of the statistical ODD. I just want to make sure that, okay, I'm not really confident about what the model is going to output, so I'm going to inhibit, switch it off. And this is where I speak about no safety impact, because I want to make sure that I'm capable of detecting this and I have the mitigation means for that. And after, there is a second monitoring, and earlier in the afternoon we are discussing about the TBS use case, where I have a distribution, but it's a long-term monitoring, so it's post-operations, I would say, where I think it's also important to verify that the distribution of the ODD that I have taken into consideration during my development is not drifting, and therefore putting my model performance because I operate much more in some areas of the domain of operations that I did not anticipate originally. Yeah. And for me, this one is not embedded. It is a post operation, and that I think we also need to put in place. That would be the two differences I would make.
Yeah. Thank you. Any other questions?
No. So let's continue with you, François, with the key takeaways and the MLEAP project next step before we close the conference.
Okay, thank you very much, Mathieu. First, I would like to thank all the presenters for all these inspiring presentations and technical aspects related to the MLEAP project on all the different tasks and the presentation of the generic pipeline that has been created during the execution of the project. I will now present you the key takeaways from at this moment in the execution of the project. When I refer to takeaways, it's not only takeaways and looking at the next steps in the MLEAP project, but also looking beyond the MLEAP project. So looking at what will happen also at the end of the project. And what I will present is mainly looking at it from an EASA perspective. There is an issue with the computer, with the Pulse Secure. Thank you. So the first set of takeaways is related to the three tasks that were presented today. And before that, I will re-insist on the fact that during all these presentations, there is something that is really considered as a centerpiece for everything related to the learning assurance process. This is the correct management of the ODD. So ODD was mentioned at many occasions, and it is confirmed to be really an element that will orient the data quality, that will orient the selection of the model, and that will pave the way to the model performance, looking at it from a stability and robustness and generalizability perspective. So now, if we look at task one, the takeaway is okay. We have a set of methods that have been presented so far. Today, the focus was only on two of them, but for the ones who already looked at the first version of the report, a lot of methods have been experimented, and now it is time that we consolidate all these methods into some guidance for the applicants. And this guidance will have to take different things in parallel. First, it is about confirming which method will be suitable depending, for example, on the dimensionality of the use cases. There are methods that will apply to low dimension use cases, whereas some other methods will be more focusing on high dimension use cases. Second, different methods have different goals. Some will indicate some weaknesses into from completeness and representativeness of the data set. Some will indicate a good achievement in terms of completeness and representativeness. So the guidance will have to provide additional information from this perspective. And then also the guidance will have to elaborate on which of these methods are suitable for an a priori evaluation and which ones are more to be used for the a posteriori evaluation. With these two notions being presented or being elaborated in the generic pipeline. So these are, I would say, the main takeaways for the task one. If we move to the task two, a lot was already mentioned in this area. So ensuring generalization remains a significant challenge in the area of machine learning. So during the first experiment, it was with on the toy use cases, it was not possible to provide a priori generalization bounds that will be sufficient to satisfy objective LM04. So we have also to investigate some other means in order to come to a consensus with this in mind. Because generalization, as it was also mentioned, is key, especially when we will move in higher criticality for the applications. The good thing is that generalization is a very active field of research, and we hope that in the future there will be some additional conclusions with regards to the elaboration of generalization bonds and so that we can increase the confidence in generalization in the early stage of a project. And from an EASA perspective, we will continue monitoring these aspects. If we move to task 3, I think Arnaud mentioned it very clearly. So we have 3 types of methods to evaluate stability and robustness. All of them have their values, their advantages, their concerns, their limitations. I will just come back to some of them. So statistical methods, they can provide, they can have value when assessing many of the properties of an AI-based system or an AI-ML constituent. However, they can be very effort-consuming, and there could have some limitations in terms of scalability with regards to high-dimension use cases. Formal methods, they seem to be very well suited for assessing the stability of a model. However, in same kind of limitations in terms of scalability that was mentioned, and probably some of the questions were related to some concerns with regards to scalability. Empirical methods, it was not much discussed, but they have clearly their value. In this area, they will really rely on the expert judgment from a business perspective and from the data scientist perspective. If we move to the generic pipeline that was presented just before, first, it is a framework that tries to organize the verification activities for any machine learning model. It introduces some a priori evaluation and a posteriori evaluation, so that's nice, and so it puts the focus on the iterative aspects of the development process, and yes. Some takeaways also from looking at this generic pipeline. First, it was mainly developed in the context of the MLEAP project, so it has put the focus on all the objectives related to the project, so data completeness, generalization, robustness. But there are some other objectives in the concept paper, and we have to make sure that these will be addressed and they will be compatible and well positioned into this pipeline. I will just give the example of development explainability. Development explainability is a huge topic as well, and it has not been addressed, so we will have to see how some practices in terms of development explainability can be mapped into this pipeline. Also, this pipeline has not been confronted to any industry framework, and this takeaway is probably more for the applicants. We know that most of the applicants will put in place some principles coming from MLOps in order to automate the development process. Now, if they want to integrate this pipeline, they will have to take into account or to think how to integrate this loop or this activity or this type of evaluation into their MLOps process. I would like now just to conclude on what are our takeaways looking at the final deliverable of the MLEAP project and position it with respect to the AI roadmap 2.0 and its implementation via the concept paper and the rulemaking that will take place from now on. So if we consider the deliverable, first I propose that we move on the right part of the slide. We will soon issue the final issue 02 of the concept paper. Guillaume mentioned that it will be end of February. I think it will be more beginning of March. But okay. So we are in the process of extracting some recommendations, some practices in order to propose some anticipated mocks in the different objectives that were mentioned during the presentation. So that's something that is in the very short term. Unfortunately, for the issue 2, it will be based on the current version of the report. So it will not be possible to wait until we have the final report, and probably that we will have more mature outcomes in May with the end of MLEAP. But I think, no, I don't think, I'm sure that we can already propose some anticipated mocks. So that's the first step. And as you know, the concept paper will be a very important asset when we enter into rulemaking. We will enter into rulemaking, I think, in the Q2 of 2024, something like that. So, but in parallel of that, because we will not have everything that is coming from the MLEAP project, that will be in the issue 2 of the concept paper. We already imagine that we will have a set of recommendations, a set of best practices that will enter some GM, so guidance material, and some AMCs as well, that could be introduced in the layer that we call AI, AMC, and GM, that is just below the AI part that we have in mind. But also, and that's something that we will discuss with EuroCAE and SAE, we think that it could be interesting for the community to elaborate on a EuroCAE report on or an AIR from for SAE that will deal with what has been delivered with the MLEAP project, and but that is to be that will be discussed in the coming months with EuroCAE and SAE. I think I am done.
Perfect. Thank you, François, for this presentation. So we are running a little bit out of time, so we will shortly close the conference right here. So if all the speakers can go on stage for for the final, and I will also explain what's next for MLEAP. Okay. So really fast. So what's next for MLEAP? So as you know, the project has been going on for almost 2 years now. So it will end in May 2024. So in May 2024, the final report will be published. So we'll inform you on when and where to find it. And we will have one more MLEAP Stakeholders Day conference, so the fourth one, the last one. This one will take place during the EASA AI Day on May 29th. And the EASA AI Days will take place between May 28th and May 29th. And so May 29th will be dedicated to the MLEAP Stakeholders Day final conference. So just a little bit of promotion, and so everything that has been done, has been said. The recordings of the different conferences and as well as the presentation will be available on the two main MLEAP pages. So one is on the EASA MLEAP pages, and the other one is on the Airbus Protect MLEAP pages. So if you haven't looked at it, please do so to check it out, and we will publish the recording of this conference and as well as the presentation on those two pages. Okay, so the conference just came at an end. So I would like to thank first of all the speakers for those great presentations. It was a 3 hours intense conference, but I think we managed it pretty well. So yeah, I think we all deserve some clapping. And also, thank you all of you for being here, either with us in the room or virtually. So thank you for sticking with us until the very end. And then we will see you very soon for the last conference in May 2024 in Cologne at the EASA. So the EASA will shortly promote and share the registration process as well as how to find the right access. So let's end the event here. So again, thank you all, and we will see you very soon. Bye-bye.
Thank you also from EASA side, and very, very much for coming. We will be here to answer questions because we had to skip the Q&A session at the end of the last bit of presentation. So we are here. And thank you. More to come on the EASA AI Days, and see you soon.